In this video, we're going to look at the final type of chemical bonds, the metallic bonds. And so the vocabulary we'll be using in this section are metallic bond, delocalized electron, the sea of electrons, alloys, luster, malleable, ductile, and conductive. Now, to recap very quickly on the covalent and the ionic bonds and how we can compare them to the metallic bonds, remember that for the covalent bond, it's particular for two non-metal elements or more. And in this, we are sharing electrons between the atoms, and those atoms are held together by bonds that we create by sharing two electrons. And we compare that to the ionic compounds where we need to have one metal and one non-metal. In this case, the electrons are transferred from the metal atom to the non-metal atom, and this creates either a positive or a negative charge in our atoms, depending if they got electrons or if they lost electrons. And they can be either positive or negative. We call them ions, positive for the cations, negative for the anions. And what holds them together is the electrostatic force between them. It's the difference in charges that holds our ionic bonds together. All right, so now the final type of bonds we haven't talked about is the metallic bond. And as the name implies, we need two metal atoms to form a metallic bond. When we form these metallic bonds, we see that the electrons are being shared between all of the metal atoms. And I know that sounds familiar to the covalent compounds where the electrons are also shared, but the way that they're shared in metallic bonds is a little bit different. So let's go ahead and look at that. Remember that for the covalent compounds, we can have two different elements here, carbon and hydrogen. And in this bond from carbon to hydrogen, they are sharing two electrons between them. And actually, they're being shared along the entire molecule. So these electrons can go from this hydrogen, they can move to this hydrogen, they can move to the next hydrogen, and this will act as a single unit in a way. If we were to have another molecule of that same compound, this is a separate unit, so that means that these electrons don't go over to the hydrogen of the other molecule, right? So if we were to draw a line here, these two are separated, they're their own individual units, even though they're the same. That's different in the metallic bond. In this example, let's say that we're looking at either sodium or lithium, some group 1 element. So these all have one valence electron. You can see that in the red with the electron being attached over to the positive um, atom. And what we see here when we say that all the electrons are shared between all the metal atoms is that this electron can really move to any other atom here in this chunk of metal. And so this is what we call the delocalized electrons. And so basically, we don't have a million different electrons here. But what we're showing here is that these electrons can move to any other atom in this chunk of metal. And now the reason that this happens is because metal atoms hold on to their electrons very loosely. So that's why they have no preference into which atom it's going to go to, and so the electrons are very easily shared between all the metal atoms. And again, this happens because of our values of electronegativity. If you haven't figured this out, electronegativity is very important for everything that we do here in chemistry. So again, these metals on the left side, they have very low values of electronegativity, which means that they don't hold on to their electrons very well, which is why they can be easily shared between nearby atoms. The explanation that we use for the metallic bonds is what we call the sea of electrons model. And when we talk about these sea of electrons, we're really talking about the delocalized electrons in our chunk of metal. So remember that these delocalized electrons, or the sea of electrons, these are the individual electrons we get from the atoms, but we're saying that those electrons are not bound to a single atom. Instead, they can move anywhere between those atoms that are still connected. And this is what holds them together. And we call it the sea of electrons because these electrons are really free moving between all of the atoms, and they're always just flowing, moving back and forth, kind of like the waves in the ocean. It's very important to understand this sea of electrons model because that's what gives us all the special properties that metals have. So let's look at that again. So here I have the model of the delocalized electrons, again, the sea of electrons, and here I have all the properties of metals. So in case you've forgotten what a metal looks like, here I have an example of this metal sculpture so we can talk about some of the properties that metals have in general. So one property is that they are very lustrous, or in other words, they're very shiny. And the way this works is that when light particles hit the atoms and the electrons of our chunk of metal, some of these electrons will absorb that energy and others will reflect it back. And that's what we see as something being shiny. They're also malleable, which means that they can be very easily shaped without breaking or shattering. And the reason for this is that the sea of electrons connects all the different atoms in our chunk of metal. So if I were to take this row of metal atoms and I were to just shift it over to the right, or if I wanted to move it someplace else, as long as the atoms are still close enough that they can share electrons, they're still held together. They're not breaking off and going somewhere else. Another property of the metals is that they can be made into wires. It's kind of like being malleable, but we give it a more specific term, and that's being ductile. So it means that it can be pulled into a wire, and it's the same property that I can stretch, I can shift these atoms to another location, but while they're still close enough to each other, they can still share electrons between them. And this is what connects them. And so, going along with wires, you know what wires are used for. You've seen them in all of your electronics, and it's because metals are very good at conducting electricity. If you ever notice that the word electricity is very similar to the word electron, that's not a coincidence. So, when we talk about electricity, we're really just talking about the flow, the movement of electrons. And metals, because of their sea of electrons, that means that they can allow the passage of electrons through a chunk of metal. So, if you can imagine my cursor here being an electron, that means that the electrons can move all the way through my piece of metal in any direction that I need. Because of these delocalized electrons, it's carrying the charge of my electrons or my electricity. Another property that metals will have is that they have very high boiling point and a high melting point, again, because these atoms are being held together by that sea of electrons. And another feature of them having another high boiling point and a high melting point, this isn't really related to the delocalized electrons, but most metals will be solid with the exception of mercury. And finally, we can talk about alloys. So, what an alloy is that it is a mixture of metals, but it's important to distinguish that it's a mixture and these metals are not actually chemically bonded. So when we do that, we see that we'll be taking properties of both different metals that we're combining, and we'll give it a new, sometimes improved properties to our alloys over our metals. So an example here that we can use is iron versus steel. And these are both made of mostly iron, that is the element iron, Fe, on the periodic table. But if you've ever seen these two metals, they act very differently. They can be used for a lot of the same purposes, but that steel is a lot stronger than iron, and we also can have stainless steel that doesn't rust the way that iron would. The reason for this is that in steel, we have carbon mixed in with our steel. And it's important to note that this carbon is not chemically bonded to our iron atoms, but instead they're being formed as a mixture. And that's the basics of our metallic bonds. And so that wraps up the three different types of bonds that we had. We had covalent bonds, ionic bonds, and finally metallic bonds. It's important to tell the difference between them. And in this next section, we'll be going over what their unique properties are for the each type of different compound.